Hi, everybody. Just welcome back to what is probably our final day on special relativity. A couple things before we get going. PLC this week on special relativity and what things look like from different perspectives and both moving and non-moving relative to one another. So have a bit of fun with that. Homework 6 is, I'm sorry, I realized I did not post it. But anyways, it's up now. So you got Wednesday next week. fairly light on um, fairly light on stuff, so should be fairly well doable. As usual, when that's due, quiz. We're gonna have a concept quiz on Thursday, just so that we keep up to date on stuff. So mark your calendars for those two things, and we will be going on from there. um, A couple of quick notes, just so that we're on the same page, remembering that I am relying on your honesty and you're on the honor system. So when you are doing work and submitting it as your own, please make sure it is your own work. Okay? Just a quick reminder on that. Let's keep moving along from the point where we were yesterday, or at least in the previous video, on, let's see, where were we? Where did we leave off? We talked about the twin paradox, and we talked about E equals mc squared finally, right? We were talking about the invariant, that's right. So when we are talking about dynamics, in other words, the idea that the momentum had to be redefined, the idea that the invariant is the mass in this case. And so when we're talking about energies and momenta, what we found was that the mass was the invariant thing. Now this, when I say mass, typically what that means is rest mass. In other words, the idea of the mass of a particle or a mass of an object is such that it should be the same no matter what it's doing, because when you measure the rest mass, that means you are stopping it and then weighing it, essentially. I know it's not really quite it, but you're massing it. So no matter what it's doing, if you jump into its frame, you would essentially be bringing the object to rest, and then it should weigh the same. I say weigh, but you know what I mean. It should weigh the same as it would if it was quote unquote not moving. But the funny thing is, nothing ever moves according to their own reference frame, right? You always have the right to say you're stationary and everything else moves with respect to you. So therefore, when you're considering a particle that has a mass, which, you know, electron, neutron, whatever you like, it has a well-known mass. If we see it shooting around doing things, right, we would say, oh, well, its momentum is not increasing the way Newtonian mechanics would tell us it is, right? And if we know that we can jump into its frame and say, aha, the rest mass is exactly what we'd expect it would be if we grabbed it and brought it to rest, well, then that's an invariant, right? Everybody should agree that, hey, if I jumped into that frame, this would be what the mass is. So that's why the rest mass is the invariant in this situation. And it gets back to the idea I was kind of discussing last time, which was there's no experiment you can do which tells you that you're in motion, because you have the right to assume you're not. If you found that your mass was different, well, that would indicate, well, wait a sec, maybe I'm moving relative to somebody else, but it never is, right? So that's the great thing. I was telling you last time that this mass, the relationship was that m squared was e squared minus p squared, in the same sense that we had an interval last time, which was t squared minus x squared, right? So the same hyperbolic geometry is at play here, because that's a hyperbolic equation, and so is this. And therefore, you'd say, okay, well, the bare minimum of the bare minimum of energy that something has is its mass energy. In the same way that we would say here, the bare minimum interval that something has is the proper time. That is, in other words, the time during which that clock didn't move. In other words, this being 0, the time is the bare minimum interval. Here, the energy is the bare minimum rest mass, which tells us that if we write it normally, like we did last time, then that tells you that the rest energy of an object is related to its rest mass by mc squared. That is the bare minimum mass that, that's the bare minimum energy that something has. And then if it's in motion, it has kinetic energy on top of that. All right. But the idea here is that you've increased the energy because of the momentum, but you're subtracting away all the momentum, therefore you should still be left with the same rest mass. That's what this is getting at. This is extremely useful when talking about unstable particles, unstable situations, such as radioactivity, for example. So examine this situation of radioactivity, where we start with an unstable nucleus. Okay, so I have this nucleus here, and it's big, it's ready to throw off some stuff in order to reduce its size, and it's going to decay. In other words, it's going to fall apart. There's going to be a small little explosion of a nucleus here, and we're going to measure what goes on. All right, so if we have an unstable situation, imagine that that's kind of like taking two, well, I don't know if you, in case you didn't have that here, let's see, suppose you take two, I would say toy cars or something like that, something where it's, they're easily movable, right? But there's no resistance to motion. In other words, it's not like a rolly car. It's not like one where you roll back and let it go and it goes. You just have it be like a Hot Wheels or a Matchbox car, right? So something like that, where what you're going to do is you're going to put a spring between them. You're going to compress the spring, and then you're going to hook some Velcro together and try to hold them, right? But the problem is the Velcro is not strong enough to withstand the push of the spring. So eventually this thing's going to go and go like this. Okay. So imagine it's kind of like two cars connected by a spring, but held together with some very weak Velcro, such that the spring is going to force these things apart. It's going to rip the Velcro and force these apart. So that's basically what's going on with the nucleus. There's a force which wants to keep a nucleus together. It's known as the nuclear force, the nuclear strong force. Okay, it's very strong. However, as a nucleus grows in size, and since the nuclear force is only so big, it only acts over such a particular range. If the nucleus grows slightly bigger than that range, all of a sudden, because the nucleus is made of positive charges, well, and neutrons, but those don't really interact in the Coulomb sense, because it's made of positive charges, the positive charges are all pushing each other away, right? So there's a push, and then there's a try to push things back together, right? There's a kind of a pull, if you like. So there's competing effects like a spring and some Velcro. In this case, the spring's going to win. In other words, the Coulomb force is going to win, and it's going to blow the nucleus apart, and some stuff's going to get ejected. All right, so imagine that we had a situation where imagine we had a situation where this thing breaks into just two pieces, right? So this thing here becomes a piece like this plus a piece like this, right? And they're, going to be moving away from each other. So this one's going to be heading off pretty fast. This one's going to be coming back this way a little bit. I go ahead and I grab these two pieces, right? I see the explosion happen. I stop the two pieces and I weigh them, or I'm using weigh incorrectly. I mass them. What I'm going to find, mass original here, call this M0, and then I'll call this M1 and M2. Okay. What I'm going to find in this case is that if I compare the masses of the two products here on this side, and I add them up, it's going to be less than what I had here to start with. And it's not going to be by very much. Really not going to be by very much. And the reason is because of the size of the c-squared. It turns out that if you consider the kinetic energy that's available to these two here, that energy had to come from somewhere. This thing was initially at rest, or if it wasn't, we jump into its frame and we're watching it. Now it's at rest with respect to us. When it explodes and these two pieces come away from each other, you'd think, oh, great, conservation of momentum, just like a 4A situation, and you would be 100% correct with that. But where does the energy come from? Well, it's as if there's, right, like a little internal spring in here which goes and pushes everything apart. But that spring, right, if I think of compressing a spring, I've done work to do that, which means I've energized the spring in some sense, right? I put energy into the spring to compress it or extend it, but that's not really this situation. But if I compress the spring, right, that means I've done work to compress the spring, which causes there to be a mass component to that. So you can actually consider this thing as having an extra piece of mass, which gets converted into the kinetic energies of these two things. Now, like I said, that mass is not very big. Typically, it's 100th or 1,000th of a proton mass, or a, is that right? A neutron or proton mass, if I think that's right. Because the value of c-squared tends to be very large. It is basically the highest speed that we know of. So when multiplying by that, it tends to make the energy extremely big, even if you started off with a very small mass, right? And this is actually what goes on. And there's a well-known decay. It's been studied. It's been analyzed with the energy mass principle here. It works out. So the idea of the energy that these pick up coming from the mass is basically where the energy of nuclear explosions comes from. So these, the kinetic energy here, it's due to a decrease in the mass of the system. Okay. But the energy and the mass are just two different ways that the same thing shows itself. In other words, we shouldn't be thinking about conservation of mass anymore, and we shouldn't be thinking about conservation of energy anymore. We should be thinking about conservation of mass and energy, or if you like, just mass energy. This should be rolled into one quantity. And it's hard to see on a scale where we live because the mass is the mass and it doesn't become energy. It's only when you get down to these types of scales where you ultimately see stuff like that. All right, so I want to talk a little bit about antimatter, and I want to talk a little bit about momentum, and then I think we'll probably move on from there into the quantum mechanics section. So I haven't assigned any particular problems on stuff like this, but it's pretty straightforward to go in and look at atomic masses because all the rest masses of all of the elements has been cataloged. It has been for years, like hundreds of years. So, well, maybe not hundreds of years, but like, okay, 100 or 150. So we know all of these M naughts and M1s and M2s. We know all of these. And slight discrepancies showing up were strange to people when they first started investigating this. And so this, just interestingly, this decrease in the mass of the system is known as the mass defect. Because originally when people found out that, hey, the mass is not the same when I add up the products and I compare it to the original, there's a defect. There's something wrong, right? There's a defect in the mass, so that's why that got that name. I want to talk about matter and antimatter because, well, frankly, it's interesting. So matter we know about. In fact, we think that most things are matter. That's not necessarily true because antimatter is essentially indistinguishable from a long way away. So what I mean by that is everything that we are in contact with is one of these, right? We're all one of them. We'll just call ourselves matter, and everything, the weird one's the anti one, right? So everything that we know about is matter. Everything on Earth and in the solar system and in our galaxy, as far as we can tell for the most part, is matter. And we think that the universe has a slight abundance of matter over antimatter because of how things started, but nonetheless, there is such a thing as antimatter. So antimatter is actually produced by these radioactive decays. And you can see it, it's pretty easy to find, because when you have a radioactive nucleus and it falls apart, it may emit a piece of antimatter, which then immediately gives off a very obvious signature, and you can detect the signature. So what does this mean? What this means is that antimatter, so what is it? First of all, it's the, let's review the fundamental particles. Well, let's review what passes for fundamental particles for us right now. All right, now there are people who study what is fundamental, what are the essential building blocks of the universe, okay? So the fundamental particles. Things like electrons, yes. Things like electrons, those are fundamental particles. Turns out that protons and neutrons are not, and they are made up of smaller things called quarks. And those things, as far as we know, are fundamental. So things like electrons are fundamental, and quarks are fundamental, right? Now, what else is going on here? Well, they have to talk to each other, okay? How are they going to talk to each other? Well, the way things talk to each other is by sending what are known as messenger particles. So if an electron wants to talk to another electron, it can do so through electromagnetic field interactions. Okay, and so as we will talk about in a little while, the electromagnetic field has a messenger particle called the photon. All they have to do is send some photons to one another, and that's how they talk. Same thing with quarks. There are also other things that they have to send. Quarks also send, they do have electrical charge, so they can send photons, but they can also send other things. Never mind what other things there are, it's not that important. But the point is that they have to communicate, and they can do so through a couple of ways. These fundamental particles all have an antiparticle. Their antiparticles are not extremely interestingly named. In other words, the electron used to be known as the anti-electron. So what is the difference here? How do you know that you have an electron or an anti-electron? Well, you look at the charge, the electrical charge. In other words, an electron as we know it is always negative. Okay? It carries a negative charge. But the anti-electron carries positive charge. And therefore, the anti-electron is known as the positive electron, which got, what is that called? Contracted even further to positive electron, positron. Positron. Lots of trons. Electron, neutron, proton, positron, lepton, pion. Right? This is all 1950s stuff. Everybody loves that. Sounds all futuristic, right? Tron. Who doesn't like Tron? So the positron first discovered in the late 1950s by a fellow down at Caltech. And how did he do it? He observed high energy particle collisions in the atmosphere due to the stuff that the sun spits out. Sun spits out all sorts of garbage. A lot of it hits us. Fortunately, we have air in the way. We have 20 miles worth of air above us trying to help shield us from the bad stuff. But we also have magnetic field around Earth, which helps kind of channel the fast-moving charged stuff somewhere else, which is great. Every now and again, one of these things will hit an air molecule in the upper atmosphere and create basically a little nuclear event, a shower. And positive electrons will be emitted as a result of that, and he was able to detect them, which is kind of crazy, but yeah. So these occur naturally. And one of the fundamental questions in physics right now, or kind of has been for a while, is why aren't there as many of these as there are of these? How come there's an imbalance in the number? That's interesting. So what happens when a positron, oh, and by the way, just to finish off this thought here, the antiquarks, those don't have a cool, nifty name like posiquark. Well, the issue here is that they come in both positive and negative charges, depending on what kind you get. There's like 6 different kinds. So you just have the antiquark. Now, what you can do is you can take all the antiquarks and build yourself an antiproton or an antineutron. Now, you can do this, right? We can fit them together to make an antiproton. And we can make antiprotons, or you can make antineutrons. Now, after finding this out, then it became a game. It becomes a game. Well, if I can make an antiproton, and we can find an anti-electron, can I make antihydrogen? Because what's an antiproton's charge? Negative, right? This is going to be a negatively charged proton. So yes, you can make anti-hydrogen. That's also been done. It's kind of fun. You go, well, how much other anti-stuff can I make? The problem is, how do you control this stuff? All right. Because the major issue that you run into with matter and antimatter is that as soon as these things touch, as soon as an antiparticle touches its matter cousin particle, they what's called annihilate. Okay? And this is a fantastic event. It's really fun. So here's your equation. This is your second grade equation here. Matter plus antimatter, which is known as annihilation. I'll just put that in quotes down here. This is a process of annihilation. Matter plus antimatter, what does it give you? Well, oops, I erased the grade equation here. That's for rest energy. Oh, what I should do is also tell you total energy. How about that? Total energy. Would look like that with the c squared. So anyways, if I have two pieces, I have a matter piece and an antimatter piece. They both have rest energy. Okay? They both have this because they have rest masses, and their rest masses are identical. The mass does not change, only the electrical charge, negative to positive in the electron case, or plus to minus if you're thinking of a proton. So the masses are equal. The charges are unequal. Now, if you know anything about how electrical charges interact with one another, unlike charges will attract each other. And that's what's going to start happening here. I'm going to have a negative electron, positive electron, and they're going to go, oh, look, the other type of charge, and they're going to go like moth to a flame, bang. So what's going to happen when these two things hit each other is that they're going to produce photons. And the photon energy, and there's going to be two photons, and the photon energy is going to be exactly equal to the energy of the rest mass of each one of these things, because they probably weren't moving that fast by the time they got to each other. Okay? So the problem, as you can see, with creating and working with a bunch of antimatter is you can't touch it, right? There's no way to, are we still good here? Okay. There's no way to physically maneuver it because everything that we have is made of matter. So if I have antimatter, I'm going to start annihilating all my antimatter with the matter. So it's not like I can grab a pair of tweezers and go, oh, look, pick up the antimatter. You can't do that. So you have to find yourself a pair of antimatter tweezers. But then you can't touch the antimatter tweezers because then your matter will annihilate with that matter. So then you have to find your anti-self to touch the anti-tweezers to make the but no, that's not true. You can't do any of that. And by the way, real quick tip, if you find your anti-self just walking around, don't shake hands. You're just going to become photons. So it becomes energy. The energy of the photons becomes equal to the rest energy of each of the electrons, positron, electron, which has same energy. And therefore, the photons are of a particular wavelength, which makes them very easy to track. Because why would a photon have any other wavelength? Right? Why would it have this wavelength if it was made from any other process? It really wouldn't. It's a specific thing, and you can track it and use it as a beacon. So when astronomers who are looking out into the universe find photons of this particular energy, they go, aha, there's antimatter over there, right? Because some just destroyed, and we just saw the evidence of that. So what happens here, literally with annihilation, the mass is gone. No longer exists. and it has become only energy. There's no mass left. Only energy. All right? Only energy. And that energy is in the form of photons. I usually just say there's a big explosion. There's a big light. It's a big explosion of essentially only radiation, of electromagnetic radiation. That's all it is. Which is great. I mean, if you're into that sort of thing. The efficiency of this is off the scale. This is the most efficient production of energy that we can possibly make. The return on this is astronomical. So if somewhere I have a table of energy by mass. So for example, if you have a battery, there's a certain amount of energy in the battery and it weighs something, right? So I've decided to take what's the energy density, what's the energy per mass in the battery. And you can do the same thing with like water going over a waterfall and turning a turbine or something like that, right? There's energy by mass. This energy by mass is the best possible situation. The mass is tiny, the energy is huge. So just to give you a bit of perspective on how much energy mass can give us. If I take an aspirin pill, okay, one of these, it could be a little caplet, something like this big, and I have an anti-aspirin pill, which is somehow getting held in space without touching air, right? Air is made of matter, it can't touch air. If I were to take the aspirin pill, which is probably like, what, 2 or 3 grams maybe, or something like that, and I combined it with this anti-aspirin pill, you could satisfy the energy requirements of the entire United States for a couple days, right? So we're talking a lot of energy getting released per mass here, okay? This situation, annihilation, gave rise to the question, could we go the other way? Can we take photons and create mass out of what seemingly was nothing? It was energy first, right? But we don't think that way. We think, oh, there's some cool stuff, and then all of a sudden some mass just pops into existence. The answer is yes. We can go backwards and do this the other way. It's called creation of matter. So we can take photons that are appropriate energies, get them to interact with each other under the right circumstances, and mass will pop out. So that's pretty cool too. All right. Okay. So, okay. Creation is it's anti-annihilation. There you go. That's the theme of the day, apparently, is photons going into matter plus antimatter particles. So I'm just going to say particle plus antiparticle here. Yes, that can be done. So it's like you can store some energy in the mass of the particles. Yes, that works. So what else is interesting here is that we have conservation of momentum, linear momentum I'm talking. Well, we also have angular momentum too. We could talk about that, but probably not going to right now. Let's just think about linear momentum such that if I looked at an annihilation event, I would have an electron here, I would have a positron here, right? E minus and E plus, those are the antiparticles, right? They're going to attract each other, and they're going to go towards each other. They're going to carry some momentum with them. right? And what's going to end up, there's going to be something happens, and then what's going to end up is basically there's going to be, if we start with them at rest, then there's zero momentum in the system initially, right? And therefore, momentum picked up by the electron to the right should equal the momentum picked up by the positron to the left. So we still are left with zero momentum in the total system, which means that the photon that comes out each direction should be diametrically opposed because they should also conserve momentum. I'm going to label these gamma because they are very high energy photons. And if you remember your EM spectrum, the gamma band is above the X-ray band. Right? You'd start with radio waves in the very low frequency, very long wavelength. You'd get up to infrared, well, it's microwaves, infrared, visible. And then above visible, you'd go ultraviolet, you'd go X-rays, and then you'd go gamma rays, which are these typically very high energy. But notice that they have to be going along a diameter, right? They have to be 180 degrees opposed to each other because the system should not carry any momentum. Wait a minute, you say, how can photons carry momentum? They have no mass. And I would say, I understand what you're saying, but don't get locked into classical thinking. We have to, remember, we have to step away from the classical definition of Newtonian momentum, right? Mass times velocity. That's not the be-all, end-all of momentum. That's just the usual, common, everyday form that people, things of our size and mass and energy can use, and it seems to work. But when you change realms, you have to develop a different understanding of what's going on. And that's what I'm kind of hoping that is one of the takeaways of this, is that our understanding of the very fast changed what we thought about the very not so fast, like us. So yes, photons carry momentum, high energy photons, and they do carry momentum. So let's talk about that, because photons have zero rest mass. And that means that classically, right, by the definition of Newtonian momentum, there would not be the possibility of them having momentum. But remember, we can't limit ourselves in that way anymore. All right? Let me give you an example of this. Let's give an example of this. Suppose that I have a train car. As always, I have a train car. And let's see, let's get rid of this so I can draw some train cars. And I have one side of it which is going to emit some photons. All right, so I'm going to draw my train car here. Let's do it like this. Like so. I've got my train car here. And the center of the train car is right through here. All right, we'll say that's the geometric center of the train car. So let's examine that. You'll have to kind of bear with me a little bit on this example, as perhaps small as it may seem. This train car is on frictionless rails. And what's going to happen here is that, for example, let's say that this side over here, it has a temperature. So let's suppose that it emits some infrared radiation. It emits some photons. Suppose I have photons leaving this side over here. Right? Photons leaving. They're going to come over here and get absorbed by the other wall. Right? What are we going to see? Well, this is basically like the situation of you're standing on a skateboard and you throw something, right? Something is now emitted from you. You throw a bowling ball or something, right? Because for us, it would have to be pretty large. Throw a bowling ball. I'm going to recoil backwards. Well, that's exactly what this train car is going to do, right? Train car is going to recoil backwards. So what's going to happen now is train car is going to look like this. I'm perhaps exaggerating slightly how much the train car is recoiling backwards due to photons being emitted by the wall. Nonetheless, the rails are still frictionless, and we don't have to worry about the interaction there. What's going to happen then is the photons get absorbed here. Photons are absorbed on the right-hand wall, right? So this does two things for us. Number one, it establishes, in fact, yes, photons do carry momentum. In other words, it's the left-hand wall, when it emits photons, right, is just like you taking a bowling ball and throwing it this way at someone who's over there. You're going to recoil backwards, and now if you're standing on a cart with wheels, right, you'd be going backwards. Now, your partner over here, who's on the same big long platform with wheels, is going to catch the bowling ball, which means that it's going to bring your system to rest because now there's no relative motion, right? There was never any momentum to start with. Now there's still zero. But what's happened? The bowling ball has changed sides of the cart. So over there is where it started, which means that if I were to have weighed the cart, if, for example, my partner and I have pretty much the same mass, which I think I do. Yep, looks like we do. Okay. I'm holding a bowling ball, which makes my side of the cart slightly heavier. So the center of mass is closer over to my side. But if I throw it over to my partner over here and he catches it over here, now the center of mass has switched over to here. But look at what's happened. If I consider the cart or the train car here to have a center of mass that was right here, that center of mass cannot have moved. Why? Because there was no external force on the train car. And that's what Newton's law tells us, right? In order to move something such that its center of mass displaces, I have to provide an external force. But none was supplied here because this is all internal to the train car. Therefore, the train car now weighs a little bit more over this side because the center of mass has, from the train car's perspective, the center of mass is now over here. Of course, to our observer, the train car recoiled this way. So if we were to, quote unquote, weigh the wheels and determine, well, which one's going to carry more weight to it, it'd be the one on the right because that's where the photons emitted. And photons absorbed. And that's why you can also say, yes, that energy of the photons contributes to a mass effect, right? Now that the photons have been absorbed, their energy is contributing to a mass effect on this side of the cart and making it weigh more. So this is not quite to scale in terms of the amount that the cart displaces for 3 photons getting emitted and absorbed, but nonetheless, I'm sure we're all working together to figure out how this whole thing happens. Okay, so anyway, this is a real effect in the sense that we just did a thought experiment about it. But our thought experiment obeyed all the laws of physics, so how can it go wrong, right? It conserved momentum and it obeyed Newton's second law. So what could be wrong with that? Center of mass hasn't moved in space, but it has moved relative to the car. So two things come out of this. Number one, momentum of photons, photon momentum. And number two, once again, I'll just say double-headed arrow, E and M here. Energy and mass playing the same type of role. This is the center of mass of the train car. All right, so photons do carry momentum, and it's perhaps a bit of a hurdle to mentally jump over here, but they do a lot, and they do a lot more than this. So I'll just leave it at that. But the physics of the situation often dictates that when you find something out and you go, oh, well, that's weird. Well, it may be weird, but it seems to be that way in order to satisfy the laws. All right, so we've got that. Let me see if there's anything else I wanted to say about any of this. I don't think so. Yeah. Nothing particular about special relativity. I wanted to give a little bit of insight into general relativity right now, just to kind of finish off the relativity topic, unit, whatever you call it. And this is not going to be, you'll never see this on a homework or a celebration or anything like that. This is mostly just for smiles and giggles, so that we can take some of the consequences of special relativity and also put that with some of the interesting consequences from general relativity. So in general relativity, let me kind of sketch out a pretty straightforward situation which helps show one of the main things that GR is all about. All right. I'm going to take the idea of a rocket ship. Okay, rocket ship here is firing its engines and is accelerating upwards. So let's suppose we're standing in here. There's a window right here, which we can look out. And I will say rockets are not known for their windows, but I mean, not on the side. They do have them in the front, but not the side. I think we're missing out on a whole new viewpoint here. Here we have the rocket. It's accelerating. Let's suppose that the acceleration of the rocket. Now, we're in outer space here, far away from any gravity. There's no big mass nearby, okay? So imagine yourself, you're out in the Star Wars universe or something like that, right? And you're just floating around. You're like, yeah, pretty cool. And I'm going to kick on the thrusters, right? I'm going to start going. Let's suppose then that I'm accelerating upwards this way at G. I'm going to accelerate upwards at G. What does this mean? Well, if I were to stand on a bathroom scale, what would I read? Well, I couldn't read my weight. That would be kind of weird, right? Because weight involves a gravitational pull on a mass. But there is no gravitation in this situation because we're far away from any masses. So really the scale is reading the force it's applying to me in order to accelerate me upwards. And that force that the scale is applying to accelerate me upwards gave Einstein what he called the most beautiful thought that he'd ever had, which is that accelerations and gravitation are the same thing. But before you go, before you understand, before you say that, understand what is happening here. Basically, when you think about the situation as it appears to this person on the rocket ship, right? The person on the rocket ship may not have any visual cues as to what's happening other than the engines are firing. Okay, fine. Maybe it's really soundproofed or something. They feel like they weigh something, right? If they stepped out of the rocket and went out onto Earth, they'd be like, oh, yeah, I'm on Earth because I feel like I weigh whatever it is I normally weigh on Earth. Then I got into this rocket ship, I weigh exactly the same. So it's basically as if I'm on a rocket ship that is still and at rest on Earth's surface when I do this, right? So in other words, this is equal to this here. Oops, no firing of the engines. There can't be engines firing. I better put legs out like that. And it's on the platform. And here's the person, and here's the window, being like that. And we are on Earth. And V equals 0. In other words, these two situations are exactly the same. This is in outer space, far from any masses. So just say no gravity here. But I have turned on the engines such that my acceleration due to the engines is exactly identical to the gravitational field strength here on Earth. Okay, this is known as the principle of equivalence. So what he said was, that's a V. So what he said was, if these two situations really are identical, then anything that happens here should happen here. And anything that happens here is also going to happen over here. For example, if I look at the scale, I stand on a bathroom scale, I read my weight in this situation, which is not really weight, but it's the force applied, then it would read the exact same thing as a scale that I would be standing on here. And yes, that would be true. Now, here, I'm going to take a ball, I'm going to drop it. Am I really? No, because the ball's going to stay right where it was, and the bottom of the rocket's going to come up and hit it, which to me on the rocket makes it look like the ball went that way. I'm going to take the time it takes for the ball to hit the bottom of the rocket. I'm going to go over here. I'm going to drop the ball again. Same thing, same height, same time. Okay, I'm going to toss the ball this way. I'm going to do whatever. It's going to do all the same stuff, right? Up, down, everything's going to work out exactly as if this was going on over here. All right, so let's imagine that we throw a ball from outside. We throw a ball from outside the rocket, and it's going this way in outer space. No gravity around, so it's just constant speed in a straight line. It goes through the window. The window, of course, was left open by a careless traveler. And as the rocket is accelerating upwards, what does the path of the ball appear to be to the person on the rocket? Okay, so here comes the ball. It's going that way. It's going to go in through the window. But as it goes in through the window, the rocket is accelerating upwards. The ball, of course, is going to travel straight. Because from our perspective, right, it has no reason to go up or down or deviate in any way. What is going to happen as the ball goes this way is that the rocket is going to go this way at an increasing speed. So you'd say, okay, what does the path look like if I'm this person on the rocket? And all of a sudden a baseball enters the window, and since the bottom of the rocket is going up, I see eventually the ball hits the bottom of the rocket because the bottom of the rocket's moving upwards into the path of the ball. So what trajectory does the ball take through here? Well, that's a great question. Fortunately, we have a way to analyze that. It's this one here. If I throw a ball through the window, we already know what path it's going to take, right? It's going to go like this. Oops. It's going to curve downwards like that. Well, you can't really see that, sorry. Well, maybe if you look really closely, right? It's going to be parabolic downwards. Therefore, that's what's going to happen here. It's going to go parabolic downwards. Okay. Cool. Well, here's a thought. What if we replaced the baseball? What if instead of a baseball, we had a light beam instead? What if instead of having a baseball, we just shined like a laser pulse, and it was traveling through space, and it went through the window, would it do the same thing? I mean, it's just horizontal here compared with the rocket accelerating upwards at g. Would it follow it? Now, it's not going to be the same path, right? Because obviously the light's way faster. But is it going to curve downwards? Because the rocket's moving upwards, so it's going to go through the window, but it still could hit the bottom of the rocket because the bottom of the rocket's accelerating upwards, like this. So from someone who's on the platform, it looks like the light's dipping, right? Oh, well, if that's happening over here, I guess that's happening over here too. Which means that since gravitation and acceleration are the same things and they produce the same results, so light is bent by the acceleration of the rocket according to the rocket observer, and according to the rocket observer, light should be bent by the gravitational field of Earth because that's equivalent to an acceleration of a rocket upwards, and we can't tell the difference. So, does light really curve? Yeah, it really does. One of the main predictions of general relativity was that this would happen. In other words, masses in space-time make big kind of differences in curvatures in the space-time. So when the light travels past, they get affected by the curvature of the space-time created by the mass. That means that light does not travel in a perfectly straight line all the time, but it travels instead along a geodesic, which is the shortest. If you know about what maps and airline pilots do, right? They never fly straight. Like on a 2D map, you go, oh, well, if I want to fly from Washington D.C. to London, well, I just have to go and I'm there. Well, yeah, on 2D paper, sure, but when you're on a globe, you have to follow the circles, right? So airline pilots always travel in a circle, well, or an arc of a circle from one place to another. That's called a geodesic. Well, light does the same thing. It thinks it's traveling in the shortest. Path, but it can't go directly there. It's got to go around because space is curved. The space-time is curved, really. So this principal equivalence leads to space-time curvature, and therefore the path of light being curved because light travels in space-time. Has this been tested? Yes, it sure has. This is the effect known as gravitational lensing. So here is a star, and then here's a very large star like our sun over here. And you'll notice that the star emits light which is bent by the sun. Okay, so if we're over here, that's us on Earth over here. This is Earth, this is sun. Right? If I'm looking at the light that's emitted by the star, I'm going to look at a couple of beams. One of them happens to just graze the top of the sun like this, but because the sun is a gravitational body, it's going to pull it around like this, and we're going to see it. Same thing's going to happen down here. It's going to pull like that, which means that from Earth, we're actually seeing two versions of the exact same star, because for us, it looks like the star is over here or over here. So we see the exact same star in two places in the sky. And then, of course, because we have the advantage of Earth going around sun, pretty soon we're going to be over here, and then we can see the star directly. And those two things aren't there anymore. But there's one star that's right there. And yes, this is a real effect. So anyway, one of the main principles of relativity is that I'll sketch out another one, and then we should probably move on a little bit here. So another one that happens, and this is a really cool one to think of because we just finished talking about special relativity. You're going to think of a turntable, right? Just your basic standard record player. And I'm going to put a clock right here. That's not a person, it's a clock. And I'm going to put a clock over here. Okay, and this thing's on a spindle. And suppose it's going to be rotating around like this. All right. Okay, so from a special relativistic standpoint, if I look at the, if I stand right here with this clock and I look at the outer clock, right? Suppose these clocks, right? I'm going to stand at the center. This is a rotating turntable with two clocks. If I stand at the center and I look at the outer clock, is the outer clock moving with respect to me? In other words, should I expect a special relativistic effect on the time of that clock based on the time of my clock? Right? I think you'd say no, because that clock is not moving with respect to me. In other words, it's always right here. And if I stand at the very center of the turntable, it's like I could put my arm on top of this clock right here, and that clock would never move from being right under my arm, right? So that's all we're doing. We're just going like this. The clock's always right there. It's always, all I got to do is look down my arm, and it's right there the entire time. So from the perspective of someone standing on the turntable, there is no difference between these clocks. However, if I now remove myself and we look at it like this, such that we see the turntable spinning, this clock, we should say, should have no special relativistic effect. In other words, that clock and us are not moving relative to one another, but this clock is going back and forth, right? And we know moving clocks run slow. Therefore, we should expect that this clock would run slower. So how can it be that one person sees no change, but one person who should be in exactly the same equivalent reference frame does see a change in the time of the rotating clock out here, right? You see the dilemma here? In other words, If I'm outside and I'm watching the turntable spinning, I'm saying this clock is in my frame of reference, but that clock is running slow. Now, if I jump onto the turntable, wouldn't I say that this clock is no longer running slow because it's not moving with respect to me? So how can we both be right? Apparently I didn't change my reference frame, because all I did was I came from outside the turntable to being on the exact spot of the turntable where there's no motion. All I'm doing is turning, right? There's no motion relative. But now I get a different reading for this clock. So how can these two things balance each other? How can they be copacetic with one another? Well, the person standing out here watching the turntable go around is definitely going to see a special relativistic effect. Right? That clock is in motion with respect to us. It must have a time-dilated component to it. Therefore, when I jump on here, I'm missing something. There must be a time-dilated component to this thing, even though it's not moving with respect to me. And there is. And the idea is that it's in an accelerated frame. So when you are in an accelerated reference frame, your time runs slower, just like moving clocks run slower. There's dilated time here. Just like in SR where we'd say moving clocks run slow. And that's part of what it is, but that's not the effect that we can use to describe it when we jump onto the frame of this, or we jump onto the spot where that clock is. What we then have to say is that from a general relativistic perspective, clocks that are accelerating more heavily experience slower time, just like a moving clock experiences slower time. So the GR perspective is accelerating clocks, because this has a centripetal acceleration to it, right? Accelerating clocks run slow. Which means that now I'm going to go back to this exact thing here, and I'm going to say, okay, whatever's true for an acceleration must be true in a gravitational field. And therefore, what you would find is that clocks that are submerged further into a gravitational well will run slower than clocks that are out in free space. That's another reason why we have to reset the GPS satellites, because they're in a slightly weaker gravitational field due to Earth, because they're a little further away from the center than we are. So in fact, the GPS satellites have two effects that are going, and they are competing with each other. We should see their clocks running slower because they go in motion with respect to us, but we should see their clocks running faster because they're in a weaker gravitational field. It turns out these two effects almost balance each other. Not quite, but almost. Pretty interesting. I also told you last time about taking a clock up on an airplane and circling around. Yeah, that was done in the late 1970s. Somebody rented a Navy plane and just circled around for like hours and hours and hours. They kept getting refills and they just turned around. So they also computed the difference that the clocks would read based on being higher up in a gravitational field as well as being in relative motion. And these two effects compete, and they both worked out to give the exact result that was observed when the clock returned to the base, to the airport. So there's a there was a movie a while ago about black holes, and there was a scene where somebody got dropped off in orbiting a black hole or something, and then some people left and then came back, and it's the opposite of that. They were outside, somebody went down to the black hole and then came back, and then the person who was left behind goes, "Where have you been?" "I've been waiting 30 years, right?" But the people in the black hole experienced it as only about a day or an hour or something like that, because the gravitational field is so much more intense around the black hole. But this person was further enough away from it such that their time differences were vast. And so actually, that was a good representation of this exact thing right here. But anyways, so there's that. A little bit on general relativity, just for smiles and giggles, like I said, a few things to think about when it comes to the weirdness of nature and the amount of time and energy that people have spent trying to think about the consequences of what it is that we see and what it is that we observe. All right, well, that should certainly be enough for you to knock out the homework on this stuff. What I'm going to start with next time is the beginnings of, well, we talked a little bit about it already, the beginnings of the photon, the idea that photons exist and are a good model to light. And what ramification does that have as time kind of goes on here and we start looking at how are photons emitted and absorbed? What does that mean about matter? What does that mean about the energies that are involved? So I think we'll call it good there, and we will pick up with that in the next class. Don't forget that, oops, I erased it, but in the next tomorrow, right, in the next day, we'll have a quiz, just a concept quiz, so expecting more like diagrams and explanations, and that will be on special relativity. So have a great rest of your relativistic day, and I will see you in the next video. All right, happy day, folks.